Good afternoon. This will be our final lecture. In this chapter, we look at the role of non-renewable resources on economic growth. Basically, there are too many people and too few resources, so the stagnation, according to Thomas Malthus, is near. Or is it? We augment the solo model with non-renewable resources. Example, oil, coal, natural gas, or gold, where E is the energy input in production function from the resource, and B is your technology, and then you've got your usual capital and population, and Y is your output. The stock of non-renewable resources, the R, is being depleted over time. And in order to determine the rate at which the stock of non-renewable resources is depleting, you divide this equation, R dot equals minus E. You divide it by R, and you'll get the rate at which the stock of non-renewable resources is being depleted. And this is this equation right here. R dot divided by R, which will leave you with minus SE. And this is shown in figure 9.1, where you can see that the rate at which the stock of non-renewable resources is decreasing. We've got a downward slope. To get the growth rate of output per worker along the balanced growth path, we divide our production function by Y alpha, and then you solve for Y, and then we do our usual mathematical trick of taking logs and derivatives, and then we'll get our growth rate of total output per worker along the balanced growth path. And what this equation is telling us is that the faster population growth combined with the finite resources, the rate at which the non-renewable resources are being depleted, will reduce growth. But bear in mind that technology is still part of your equation. We can also calculate the drag on the growth rates coming from the finite resources. But for this, you can self-read. So if non-renewable natural resources are becoming more scarce as more are being used up, then their prices should be on the rise, according to economics, right? However, empirical evidence goes against this. If we look at figure 10, which plots the price of fossil fuels relative to wages in the US over between 1949 to 2010, you can see that the price of fossil fuels in 2010 is relatively similar to the price of fossil fuels in 1949. And in addition, if we combine that analysis with figure 10.3, which shows you the price of commodities relative to unskilled wages, you can see that the price is declining. Combine it as well with 10.4, where we have the factor share of energy in the US economy. Again, you see that the share of energy in 2010 is relatively similar to the share of energy in 1949. But when you look at the per capita energy use in the US economy, that is on the rise. So if prices of non-renewable resources are declining, yet more of these resources are being used up, and they haven't run out yet too, how to explain this conundrum, which goes against basic economic theory? Your demand for these resources is increasing, the supply is decreasing, but the price is low. We know that economic theory states that the price should be high. One way of explaining this is to use a different production function. Instead of the conventional Cobb-Douglas production function, we introduce the constant elasticity of substitution production function. And with this function, the substitution of non-renewable resources becomes easier. For example, new deposits of resources are always being discovered. You can think of the fracking that is taking place, well, that is meant to take place in Karoo, but there's still some controversy against it. And technology as well is still part of the production function, which means that better technologies are going to offset the decreasing returns that are coming from the non-renewable resources. Example, scientists keep coming up every time with more efficient use of technologies where they are harnessing renewable resources such as solar, wind, and water energy. And therefore, we are becoming less reliant on these non-renewable resources. Another consequence of using non-renewable resources, apart from depleting their stocks, is the damage it does to the environment. Fracking or drilling for oil disrupts ecosystems. The oil that we use in fuel contributes to air pollution as well, as it is used for cars. There is therefore a trade-off between producing goods and services and the damage we do to the environment. Is there an environment Kuznets curve, where initial increases in GDP will increase pollution, but as GDP continues to rise, the economy becomes rich enough to come up with more efficient technology that creates less pollution, and so your pollution starts to decline. This is witnessed or seen, the evidence is seen in figure 10.6, with air pollutants declining over time in the United States. So in conclusion, as long as technology grows at a faster rate than we use up resources, it will offset the diminishing returns by relieving the population pressure on the finite supplies of these non-renewable resources, and we should therefore generate enough growth. This is a short summary of chapter 10, and in conclusion, chapter 11 is just a conclusion of all that we've covered, all the chapters we've covered to date. Why are we so poor and they so rich? What is the engine of growth? Why are there growth miracles and disasters? Countries that invest in more physical and human capital have high levels of skill and technology, have strong institutions and social infrastructure that encourages skill accumulation and attracts investment, are open, they are richer today, they are more developed, and they grow faster. Innovation, inventions, ideas, whatever you want to call it, this is the engine of growth. As long as countries encourage innovation, growth will increase. And good social infrastructure provides the right incentives for growth and prosperity, leading to growth miracles. Thank you.